on the stellar evolution is given by the electromagnetic radiation, and that is used as the messenger. So that is the entire crux of this talk. So why do we use electromagnetic radiation as the messenger? Just because we cannot travel beyond our solar system. Okay, and we'll be, as I said earlier, I am more interested in looking at the stars within our Milky Way galaxy and far beyond. So the only way I get the information from those stars is through the light, and so we can't travel there. Another thing is that we can't, once we travel there, only we can bring the samples from there. So that is also ruled out, and we can't perform any experiments going to those stars. So the only way to get information is through the light which those sources are emitting. Okay, so astronomers receive only one thing from the universe, that is the light. So light gives all the information. Light, I mean the electromagnetic radiation, gives all the information about the stellar evolution. Okay, now I said that we can't travel to even the nearby star. Let us get a feel of the distance. So space is really big. So assume the distance between Earth to Moon. So if light has to reach from Moon to Earth, it takes only 1.3 light seconds, which translates to these kilometers. And similarly, if you see Earth to Sun distance is 1.4 into 10 power 8 kilometers, but light takes only 8 light minutes. So once a photon is emitted from the solar photosphere, it takes only 8 light minutes to reach us at the Earth. Now let's go a little beyond our solar system. The nearest star to us is Proxima Centauri. Okay, it is at a distance of 4.2 light years, so a light which is formed on the surface of the star, in order to reach Earth, it takes 4.2 light years. So imagine what is the distance. So look at the distance. It is 40 into 10 power 12. So which means after 40 zeros. Okay, such a huge distance you have. Okay, now let us assume little beyond, let us go little beyond, like our galaxy is Milky Way galaxy. So from we are in the spiral arm of our galaxy. So from one end of the spiral arm to the other end, in our own Milky Way galaxy, so look, it took something 100,000 light years. Okay, which translates to 1.9 into 10 power 18 kilometers. Really huge. So going there, getting samples is out of question. Okay, so astronomers even go beyond this. So for that, even the light years sometimes becomes small considering the distance. So we use another parameter called parsec. So one parsec is called 3.26 light years. So in a nutshell, if you see, only light is the only messenger that can cross all these distances. Okay, now always mankind has a curiosity that are we alone in our entire in our galaxy or in the entire universe for that matter. So so if we want to study about the astrobiology, is there any life out in other stars or in other planets, which has been almost more than 6,000 exoplanet has been detected. So is there a life over there? If you want to study, then those information again comes from the electromagnetic radiation, which is the light. Okay, so what we know, there are thousands of planets, which means, to be precise, it's something like 6,000, and the number is even more than that. So in order to life to exist, we need liquid water. So all this information comes from the electromagnetic radiation which we get to see in the earth. Okay, so these planets form naturally with the star. Okay, so if you take the star formation as a process, this planet form along when the star itself is formed. If you take our own planet, like our own solar system, when the earth is when the sun is formed, along during that process itself the planets were formed. Okay, so how do we search for life? Like if I want to study, say, 6,000 planets are out there, is there a life over there? Now how do I study from electromagnetic radiation? So there are some, we cannot travel there, and light brings the clues for that. Okay, so the one way to study is that spectroscopy of the planetary atmosphere. So out there is a planet in the other star. So if we can do a spectroscopic study of the planetary atmosphere, then we can tell whether there is a possibility of life over there or not. Okay. Now, what is spectroscopy? Will, as the talk progresses, I will be telling you. Okay. And what are the possible signatures in this spectroscopy? What do you see? Or what are the biomarkers which tells you that there is indeed a life over there? Okay. That is, look for oxygen and look for methane. So if the atmosphere of the exoplanet has oxygen signature and methane signature, then there is a likelihood that okay, so there is a likely signature that in fact there can be a life. Okay, I can, it's not for 100% also. So I can, because we are not essentially going there to check out that. Okay, so why methane and why oxygen? See, our Earth has an atmosphere, right? You know that in the earlier talks Sir was telling about troposphere, stratosphere, biosphere and things like that. Similarly, you have an atmosphere in the planet which is hosted by other stars. Okay. So I mean planetary atmosphere of those stars. Okay. So now if you see the biosignatures are oxygen and methane. The reason why oxygen and methane is chosen is that methane is produced mostly by the microorganisms. Okay, and oxygen is mostly produced during the photosynthesis. Okay, so these two are considered to be the biomarkers. If you get some signatures in the exoplanetary atmosphere of oxygen or methane, then there is a likelihood that there is indeed a possibility of life over there. Okay, and there are other habitability markers, which means that it shows there is a likelihood that there can be life, which is the planet is habitable, which means that it is at a right distance away from the star where liquid water can exist. Okay, so those signatures are usually the water vapor signature. So if you get in this spectra some water vapor signatures, then you get the habitability biomarkers. Okay. So okay, so now this is one way of looking at whether life exists out there or not. Now there is another way. Actually, this is if assume that there is a life over there, and assume that the civilization over there is much more advanced are, it's almost like our civilization, which means it's technologically advanced. So in that case, we look for some extraterrestrial intelligence. Okay, so NASA has a dedicated survey for that. It's called as SETI, which means Search for Extraterrestrial Intelligence. So what they do is there is two kind of SETI. One is that optical SETI and one is radio SETI. So in radio SETI, what they do is they will be looking at the entire sky for some possible signatures which are given by the aliens. Okay. Still the search is going on, and similarly optical SETI thing, but we will be sending some we'll be looking for some hyper laser signature from the aliens. So the search continues. Still we are still listening. We have not yet got any conclusive evidence that in fact there exists an advanced civilization of alien elsewhere in other planets. Okay. Okay. Now everything is fine. Now we have to collect light from the stars or the planets, which is very, very crucial. Okay. Now how do we collect the light? So there are telescopes meant for this. So the telescope is nothing but this is a telescope. Okay. This telescope, probably it is a 10-meter class telescope, which means the diameter from here to here, if you go, it is it is like 10 meter. Okay, it's like, imagine that your eye is now 10 meter. Your eye is so big that it is 10 meter. So what happens? You can even pick the faint signals, are the very very low intensity signals which is coming out from the other stars. Okay, the problem with this kind of study is that because you are looking for very, very faint signal, that you have a bright star and there is a planet around that. Okay, what happens is that the planet itself can't emit. But so you are trying to find some signatures of that. So you are essentially looking at you are looking for very, very faint signals. So your telescope aperture should be very large. So the telescope gather more light than our eyes. So in fact large mirrors are required for that. And if you take the angular resolution, it is given by a simple formula 1.22 lambda by d. Lambda is what you are the wavelength you are looking at, and d is the diameter of this mirror. Okay, so people use different kinds of material for the mirror. So one thing is the zero door, which has the thermal coefficient of expansion is almost zero for this kind of material. So this is essentially to give a feel of how light is collected, and that is fed into the spectrograph to see the faint signals. Okay. Okay. So again, the telescopes can be of like different types. So one is the refracting telescope and the reflecting telescope. So this one is a refracting telescope. A refracting telescope you might have seen, like most of the amateur telescopes are refracting, and reflecting is this one. So here you can see this is a mirror. Okay, this in the refracting type you have lens kind of thing. Here it is a mirror, and this is a radio telescope. This is from GMRT. So this is called Giant Meter Wave Radio Telescope. Okay, this is in Pune. So it looks at the faint radio signal instead of the light. Okay. Essentially, again I said that in the previous slide that angular resolution is very important. What angular resolution means is that if there are, like, you two are sitting together, like I am at a very far distance. If I am at a very far distance, I will be essentially seeing you two people as a single person. Okay, now if I have to see your two as an individual person, then the light collection should be more. Okay, so this is what angular resolution means. Okay, so for optical telescope, this is. So for optical telescope, essentially, you get a very good resolution. But for radio telescope, since the operating, the lambda is like 1 meter, your angular resolution is pretty bad. So what we do here is a technique called aperture synthesis. So in this aperture synthesis, what we do is the telescopes will be like, there are many telescopes which will be arranged in a Y arm, and we'll be looking, we'll be assume that you are looking at the looking from the space, that is on the source. So we will use the rotation of the earth, and we'll presume that the distance between the last telescope in the Y arm and the other is, if it is 40 kilometers, essentially it will look, it will give a resolution which is equivalent to a telescope of like 40 kilometers. Okay, in case the Y distance is distance between the various baseline is 40 kilometers. So thereby you can enhance this value, that is 1.55 degree, to this particular value at radio wavelengths. Okay, now coming to the optical telescopes, or for that matter even infrared telescope. This is a schematic of how a telescope works. So, so you see that a parallel beam of light comes from the star. So since the star is at a very what happens is that we can approximate that the light coming over there is always parallel. Okay, now once it falls on, this is the mirror, and the primary mirror is parabolic in nature, you can see like this. Okay, and then it to the secondary mirror, and this F is called as the prime focus. So if you don't put this mirror, is that light rays, after getting reflected here, it will fall this point F. Okay. So you have to put the imaging device or the spectrograph over here. So to avoid that, what they do is, this is a comfortable position. So what they do is, they put a hyperbolic mirror here. It reflects back at the back. Here there will be a hole over here. Okay, this type of configuration is called Cassegrain configuration. Okay, so you have a primary mirror, secondary mirror, and a detector. Eyepiece can be replaced by a detector. This is how a simple telescope works. Okay. Now, now you can see that there are many observatories in India, but you can see that most of the all the observatories are in fact on the mountain tops. Okay, this is the Hanley Observatory. It is of course in Ladakh, Hanley it is. Again, it is at a, the altitude is pretty much high, and why they choose those kind of higher altitudes? It's just because the atmosphere is thinner over there, and thereby the distortions which we encounter due to the turbulence of the air will be very minimum, and the water vapor will be very less over there, because especially if you are looking at the infrared wavelengths, these infrared radiations are very much attenuated by the water vapor. Water vapor absorbs them, and if you go to the higher altitudes, again less light pollution is there. Right now people are using rampantly this LED lights, and it kills actually the faint signals coming from the cosmos. And another more important thing is that we do get very clear nights over there. So the take-home message is that higher the altitude, better the image quality. Okay, this is again observatory at Mount Abu. It is at Rajasthan, and it is at a height of something like 1,600 meters above the mean sea level. Okay. Okay. Now, what are the major ground-based observatories in India? One is in Mount Abu. It is being operated by Physical Research Laboratory, and the other is by, there are various, like you can see that Vainu Babu Observatory. It is being operated by Indian Institute of Astrophysics. again giant meter wave at NCRA, it is at Pune. Then Devasthal Observatory, it is at Aries. And you can see that there is this Indian Astronomical Observatory, which is also called as a Himalayan Chandra Telescope. It is being operated sitting in Bangalore. Okay, so people doesn't essentially go for observation to Hanley. They sit in Bangalore, and satellite link they operate the telescope. Okay, now let us slowly jump into the other wavelengths. Like right now we saw mostly the optical wavelengths, which our eye is sensitive, and the near infrared wavelength. Let us go to the other wavelengths. There is a reason for that, why we are for a multi-wavelength, which I will tell you later. Okay, now the see, look at this this cartoon. You can see that. See, this is the our atmospheric transfer. Okay, so see that gamma rays, X-rays, ultraviolet rays are completely blocked by our atmosphere. Okay, this is the optical wave. So this can be observed. This comes to our ground. That's why ground-based observatories look at optical wavelengths. Okay, now let us come to this mid-infrared part. Here lambda is increasing this way. So see, come to the mid-infrared part. In the mid-infrared part, you can see that again light is completely absorbed by our atmospheric constituents. So only way to observe these signals is to go outside our atmosphere. Okay, so that's why if you see that for gamma ray, if you want to observe, and X-rays you want to observe, we need to have a dedicated observatory above our Earth's atmosphere. Okay, similarly, if you want to look at mid-infrared wavelengths, there is a satellite called Spitzer and Herschel and many other things. So again, it is again put above our atmospheric this thing. And here, see the radio wavelengths. It is completely transparent. Okay, so that's why GMRT, which is again at Pune, it observes from the ground. Okay, now there is another important reason why we prefer space. Because you can see, if you have your satellite or your payloads over there, there won't be any distortion due to any means. So, imagine, see, this is the same field. This is from a ground-based observatory, and this is from the space. You can see much more elements here. It doesn't come to the which is otherwise not seen in the ground. See here the clear images. Here it is pretty much distorted, but here it is not. Okay, that's another reason why we go for the space. Okay, now we talked about various wavelengths, and as I introduced in the talk that light is used as the messenger. So now let us come to the actual act. What is light? Okay, light is an electromagnetic radiation that carries energy through the space. So this is the velocity, 3 × 10⁸ meters per second. It does not need a medium, because if it would have needed a medium, it won't reach us. Okay, it has wavelength and frequency. It can behave, it has dual nature. It can either behave as a wave or a particle. So if you think this light as a wave, then this diffraction, interference, it takes the wave nature of the light. And if you take photoelectric effect, like when light falls on a metal and it ejects out an electron, which is called as the photoelectric effect, then we consider light as a photons, okay, packets of energies. Okay, then it is called as a particle. So this is essentially the electromagnetic wave. So it has the magnetic and electric field, which is orthogonal to each other. Okay, now this is the same, like see the electromagnetic spectrum. This is meter waves, okay, right from radio, you go up to the gamma rays. Okay, so essentially we are trying to get information from the star in all these wavelengths, right from starting from radio to gamma rays. So each wavelength region gives various physical processes taking place in the star. Okay, so what is that? So I'll be telling in the next few slides. Okay, now as I said earlier, we can study planetary atmosphere with a spectroscopy. So what is a spectroscopy? So the spectroscopy is nothing but when you send a white light through a prism, what prism does is that it spreads into the components of the light. From you get VGR essentially. So this kind of study is called a spectroscopy. Okay, now so in the down below cartoon you can see that. So if you essentially are sending like our solar like a solar white light into a spectrograph, you get the spectrum like this. So, absorption features are from the photosphere of the sun, and so when you try to fit a black body with that, do you all know what is black body is? Okay, so black body is then Wien's displacement law. Okay, like so essentially if you are trying to model this observed and if you fit a black body, then you essentially get the temperature of the photosphere of the sun, which turns out to be roughly 6000 Kelvin, that is 5782. Okay, so these absorption lines tell what are the elements present in the photosphere. So this gives the fingerprint of the star. What are the elements over there? So, so these things are very, very essential. So as I said earlier that we are looking for the exoplanetary atmosphere. Those planetary signatures are something like this coming. Okay, so we have to use a very high resolution spectrograph to get the spectrum. Okay, so what do these spectrum essentially reveal? So it reveals what are the elements present over there, and what is the temperature, what is the motion, whether it is coming towards you or whether it is receding from you. So those kind of information is called as the Doppler shift. Okay, Doppler shift is nothing but if the source is coming towards you, it is called as blue. And if it is going away from you, then it is called as redshift. Now, how do you find that whether the object is coming towards you or going away from you? So for that, you can use this formula. That is delta by lambda is equal to V by C. So what is delta? So what is delta lambda? So if the star is static and it is not moving anywhere, then what happens is that a particular spectral line will exactly form at lambda. Now if coming towards you or drifting away from you, how much it drifted from the rest wavelength, that is called delta lambda. So from that you can tell exactly that whether the star is coming towards you or moving, receding away from you. So now various things are being like we have a spectroscopy and have done some kind of imaging of the star. So everything is done. Now what lies ahead is to find what is the age of the star, because age is very important to study the stellar evolution. Okay, stellar evolution indirectly means what is the age of the star. Okay, so this is done from this something called the HR diagram, which is called Hertzsprung-Russell diagram, named after the scientist. And they are coming. Okay. Okay. Okay, so this HR diagram essentially gives the age of the star. So essentially this is again I am reiterating the same thing. So this gives information, temperature, composition, motion, and the distance, and to the age of the star. So now the important thing is that not all all light travels the same way. Now, if you imagine that if you are going in a car and it's a foggy day, so your the headlight which you are putting, it goes only a few meters, whereas the Wi-Fi or the what do you call or the radio wavelength which you are observing, it is not attenuated, but you can see that the optical light is completely attenuated. Why is that? Because that lies, it is just because of the wavelength we observe. Okay, because optical radiations are attenuated much more than the radio wavelengths. So essentially radio wavelengths is not attenuated at all. That's why those radio wavelengths which I showed in the transmission curve, it comes inside the earth. Okay, so the result is that now certain star form, usually stars are formed inside the dense molecular clouds, so so you have to see through the cloud, so optical wavelength doesn't come piercing those dense clouds. So with optical light we can't study star formation at all. So the only way we are left out with is with a radio and infrared telescope that reveal the hidden star within the cloud. Okay. So now let's coming to the actual story, that is star formation. So how the star formation occurs? So essentially the stars are formed in the dense molecular cloud, and thereby it evolves and finally planets form around the star. So how does that happen? So see these cartoons. So this is the molecular cloud, and see this is how wide it is. It is given in an astronomical unit, and then this cloud encounters some kind of supernova perturbation, and it forms some kind of clumps which is otherwise called as dense cores, and then those clumps start gravitating on its own, and this is called as the gravitational collapse, and see the distance considerably reduces, and then what happens when the perturbation occurs, the cloud starts spinning around. So what happens, the material in the cloud forms a disk around the central star, which is called as the accretion disk, and to conserve the angular momentum of that, the bipolar outflows are formed, and then finally a T-Tauri star is formed, and when the T-Tauri star evolves further, what happens, the bipolar outflow stops, and essentially the disk is cleared a bit, then finally a young stellar system is formed with a star at the center and the planet moving around that. So essentially you can see that the during the star formation itself, the planets are formed. Planets are also formed along with the central star. So imagine, see, this is a molecular cloud. Actually, there are many star formation processes going within this cloud. We are essentially seeing through the cloud. So if we, this is an optical image, okay, which our eye is only sensitive. So if you want to see through the image, then you need to go at other wavelengths, like be it radio wavelengths or infrared wavelengths. Okay, now I just told you that we can see through the cloud. So imagine, so see these pictures. These are essentially taken at various wavelengths. This is at a visible wavelength, which our eye is sensitive to, and this is at a radio wavelengths. So you can see that, at radio wavelengths, this is completely dark, this is completely opaque. You can't see anything at all. But at a radio wavelength, see, the same thing, same field. So essentially you are piercing inside that, and you can see the some various star formation mass of the initial star. Okay, so if it is a Loma star, then after the red giant phase, it finally becomes like see here. It is a sun-like, so a protostar is formed, then it becomes a main sequence phase, then it becomes a red giant phase, then comes a planetary nebula phase. But there are many phases within in this region also. Okay, which I will be coming later. Okay, so if you are coming to this during this phases, what happens is that it loses lot of mass into the interstellar space. So these mass actually enrich the interstellar medium with higher mass elements. Okay, so we as a human beings, like we are all made of stardust. Okay, so these kind of stardust are sent to the interstellar medium before this planetary nebula phase, which will be coming a little later actually. So once it becomes a planetary nebula phase, then it becomes a white dwarf. Again, it depends on the mass. If it is a low mass, like our sun-like star, then it becomes a white dwarf. Then if it is an intermediate star, which is 2 times to 8 times our mass of the sun, then it becomes a neutron star. Then if it is a very high mass star, then it becomes a black hole. So now you need to know what a white dwarf is, what a neutron star is, what a black hole is. Okay, now what a white dwarf is? White dwarf is nothing but it's a dead star. So once if a energy is not produced, then the star can't hold itself because gravity tries to compress that. Okay, now it compresses too much that now the electrons within the star, which obeys Pauli's exclusion principle, tries to stop the gravity of the crushing. Okay, so it stops there, then it is called as white dwarf. Okay, now if the crushing again continues and these electrons and protons combine together to form neutrons, it crushes like that, then it is called as a neutron star. So those things happen if the mass is this much. Okay, and again if the mass is more, even neutrons are crushed together and it forms a singularity. It is called as a black hole. So if black hole is there, nothing is emitted. Okay, now all this is fine. Now when nothing, I said that light is the messenger. If light is not emitted, now where is the messenger? Messenger is missing. There lies the crux. Actually, now how do we detect a black hole is really there or not? So it's very simple. Like if you have, usually nature does this way. Nature doesn't either form the stars or the stellar evolution doesn't take place in singularity, which means our sun is an exception. Okay, otherwise mostly it is in binaries. So there will be 2 stars near to each other. So there are so here there are 2 stars. Okay, so one is a neutron star or a white dwarf, and the other is a normal star. Okay, so what happens is that since this is a very compact object, which it tries to steal matter from the normal star, and this lobe is called as a Roche lobe. Okay, so essentially material can't just like that go there. What it happens is that it essentially fills this Roche lobe and then falls into the star, and it becomes a accretion disk is formed around that, and essentially the presence of a white dwarf, which otherwise we can't see, is revealed, because there is something called the Chandrasekhar limit. You might have seen, you might have studied that 1.4 times the solar mass is the maximum mass of a what do you call a white dwarf. Okay, so those stars essentially emit very weak light. So once it is stealing matter from here, then if you keep looking at those things, then you can essentially see there is a variability in the brightness of this star. Thereby we can infer that there is a white dwarf or a neutron star along with that. Okay, so this is what. So this is how you detect either white dwarf or neutron star, or for that matter, even a black hole. Okay, now let us assume that if our sun is, if it becomes a white dwarf, right? Say, what will be the size of that? Okay, so it will be almost the size of our Earth. So which means that such a huge body is compressed to the size of our this thing. So it is essentially that's what it's called as compact object. So how do we detect black holes? As I said earlier, this is again the same thing only in a X-ray binary. This is what happens. It emits X-rays and other UV radiations due to this. And this is another important thing. Like, say, if two black holes interact, what happens? Okay, if two black holes interact, it essentially moves around each other for a while, and then it merges with each other. Okay, so in that process it gives a lot of gravitational waves. So those gravitational waves can be detected in our Earth. So that is using a project called LIGO, which I will be coming later. So with those LIGO project, we can say that out there is two black hole is merging, or a neutron star is merging. These kind of studies can be done. So how do we detect the black holes? This is the, just now I said that LIGO is the solution for that. So essentially LIGO is a project, it's a very ambitious project. So LIGO contains, what is LIGO? LIGO contains nothing but a high power laser over here, and this is a kind of interferometer where you have this it has two arms. This is from here to there, it is 4 kilometers, and again this is 4 kilometers. So what essentially happens is that this is now when two black holes merge, this compact object has a property space-time. So space-time is nothing but when you have a compact object, it curves the space around that as well. Okay, so when it merges, huge amount of energy is also liberated. So essentially those energies are liberated out as gravitational waves. So we have two such LIGO observatories in US, one in Washington DC, and the other in Louisiana. So what they essentially do is look for, when these merge together, what it happens is that it stretches the space-time. So when the space-time is stretched, the distance between these baselines changes in the order of 1 by thousands of a proton size. Very small changes, you can notice that. So those things, what happens is that if there is no gravitational wave coming, then what happens is that these waves goes here in the mirror and reflects back. Here it goes and comes back, and then you encounter a destructive interference. So if a wave in fact comes and hits the this arrangement, then what happens is that the one of the space-time gets stretched. So either this baseline is elongated or it is compressed a little bit. Thereby the laser light goes here and comes back, and it gives a flash of light. No destructive interference will be there. There will be a constructive interference. So if you see such a thing, then it is we can say that there is outright there is a gravitational there is a merger of a black hole or a neutron star. So this LIGO project is coming in Pune. So this is the world's third observatory. Okay. So why they are putting in Pune? The reason being that the merger of these black holes are occurring in the sun, occurring in the sky. So using triangle method, you can easily where it is. Essentially now whatever I can slide, like if you want, like in infrared gives wavelengths gives star formation, optical spectrum you can study the main sequence space, and if you are doing spectroscopy in composition, if you are looking at the Doppler shift from the spectroscopy, then you can study the motion, and if you are looking at X-ray wavelength, then you can study the neutron stars and black holes. Essentially, see, what is the thread which is connecting all these things is the light. So light is the messenger for everything. That is the crux of this slide. Okay, and now as I said earlier that we are made of stardust, that is because during the later part of the stellar evolution, like during the there is a phase called the AGB phase, wherein material are thrown out into the interstellar medium. Essentially it will throw like mostly this kind of carbon atoms, carbon, oxygen, nitrogen and iron. So these materials either form as a second generation star, or it forms new planets, or eventually it makes human beings like us. That's why there is a high probability that life can exist somewhere else in the universe. So light is essentially the messenger of the universe. From tiny photons reaching us, we are essentially studying how a star is born, how they evolve and how they die, as a white dwarf, neutron star, or a black hole. So from light we measure all these things. So essentially, the telescopes aids us to study all these things. That's how we proceed this kind of study. So essentially, the take-home message is that we are made of stars.